All right, fantastic. All right, well, thanks again. I'm really delighted to be presenting for the Winter School. I generally I love these schools. I've kind of presented at a couple of summer schools on soft robotics as well in the past, and so these are really good venues to kind of dig a little bit deeper in some of the topics. So what I actually plan to do for this presentation is actually to not spend as much time on my own research, but instead to kind of give my own just kind of more high-level perspective on what I think about soft robotics and kind of what I think of some of the important foundational principles in soft robotics that have been really helpful to me in terms of the research that I do and also how I think about design and problem solving. And then also I wanted to spend some time talking about entrepreneurship and ways of commercializing a lot of the different material technologies that have been developed within this field. So I'll be kind of jumping from topic to topic and trying to cram in as much as I can within this hour. However, with that said, please stop me if you do have questions. Don't necessarily need to go through all of this content here in this next hour. First and foremost, I do want to acknowledge my research group, the Soft Machines Lab. Although I won't be spending too much time talking about the work in my lab, I still do want to acknowledge all the folks here. This is a pre-pandemic photo. The lab has changed a bit in more ways than one over the last couple of years, and we have some new faces joining the group. But the important thing here, though, is that everybody's been able to kind of work together from very different backgrounds. It was a very interdisciplinary group, and that's, I think, led to some really exciting collaborations and opportunities. Just a quick note about Carnegie Mellon. We're in the northeast of the United States in the city of Pittsburgh. Here's our beautiful campus here. It's kind of situated next to one of the major city parks. And right now we're working out of temporary lab space because our old building got demolished. They're going to be building a new department and lab facility for us. So for the time being, we're kind of in this transition type stage. But nonetheless, we still have been able to stay productive to whatever extent we can over this past period of time during the pandemic. Just again, a little bit more about robotics in Pittsburgh more generally. A lot of the kind of exciting things that we're seeing within this region really have spun out of the work out at Carnegie Mellon, and so there's a very rich history of robotics at CMU, starting with work, for example, by Mark Rayburn on legged robots, basically the platform for the robotic systems at Boston Dynamics. And then there's been a tremendous amount of work with autonomous vehicles, starting with pioneering research with using autonomous systems in a nuclear meltdown site. And then also with, in the US, we had this big DARPA-sponsored challenge for autonomous vehicles, driverless cars, and also with humanoid robots, for which CMU has performed well. And so as an outcome of that, there's, in addition to a lot of the exciting projects and research efforts, there's been a startup and entrepreneurial ecosystem that's developed in Pittsburgh around robotics, and really leverages a lot of the work, not just at Carnegie Mellon, but also at University of Pittsburgh and other academic institutions here. This graphic is a little bit outdated. I mean, Uber ended up getting their driverless car subsidiary ended up getting sold to Aurora, a local company, but they're still very active in Pittsburgh. Now, not without going through kind of this list in detail, a big thing that stands out is that none of these robotic companies do soft robotics, right? And so soft robotics, although it's gained tremendous attention and made huge impact within academia, it's still kind of in its early nascent stages in terms of spinning out into industry and the commercial sector. There have been some really nice highlights, and I'll talk about that towards the end of this presentation on some companies that have been really kind of pioneering the use of soft robotics within industry, but there's still tremendous room for opportunity here. And so hopefully some of you get inspired to also pursue entrepreneurship and advance some of these material technologies. Okay, so like I said, I mean, there has been really big impact. I mean, this is a graphic from a review paper that I was involved in with Elliot Hawks and Mike Tolley. But by every metric, I mean, there's just been tremendous interest and growth in recent years in soft robotics, and there's a variety of reasons why. I mean, I won't get into kind of all those details. But on the left, you see just this exponential increase in journal publications, and on the right, we also see this really impressive rise in the growth of companies. By the way, just real quick, I mean, I have this bar, I can't make it go away in Zoom, that's kind of obscuring the top of my screen. I don't know if on your guys' end, are you able to see the title bar, or is it being obscured?
Yes, so we can see the title, which is Soft Robotics Trajectory of the Field. So.
Oh, fantastic. Okay, great, awesome. So anyways, and so we'll get back to what this growth means for the field, and also how you can leverage this and take advantage in your own efforts. All right, so before I kind of delve into the main content of this workshop presentation, I do want to make a few high-level comments about just basically are soft robots robots. So I'm not really the best qualified to make this to make this assessment. My training, my PhD work was within a robotics lab. But I mean, it's such a broad and diverse field. I don't know that really kind of anybody within within soft robotics. I mean, I'm sure there's a few out there who can kind of probably have much stronger ideas about what they view as kind of a robot versus not. What I can do is reference. In the United States, we have our National Science Foundation, one of the premier funding agencies for academic research, and they do have a clear definition of a robot. And so what they define a robot to be is basically intelligence embodied in an engineered construct. And intelligence is kind of what you expect, within a robotics context, right? Ability to solve problems and make contextually appropriate decisions, process information, right? So there's kind of a sensing and processing element to it. And then the engineered construct, that relates to the physical kind of embodiment of the robot, its ability to sense and move in an environment, and in some cases, alter or perform work on its environment. Okay, so, and it's up to you to decide whether some of the soft robotic systems that we've seen within the literature really satisfy this definition of both intelligence and an engineered construct. Certainly, these are engineered constructs. I think they're certainly capable of moving. But the question is, do they satisfy this definition of intelligence? And kind of going further here, we can kind of think about conventional robotics and kind of the scientific or disciplinary foundations of the field. So you can kind of think about these as the different pillars of robotics. So there's perception, cognition, control, kinematics, and of course mechatronics. Features as a very important pillar within the field. And when it comes to soft robotics, a lot of these elements do remain pillars of the field, but there is, of course, this strong emphasis on the use of soft materials. And I would kind of in bold here say that a distinguishing feature of soft robotic systems is that functionality is dictated by the mechanics and physics of those soft materials. Okay, so, and I would go further and say that not all soft robots are robots, at least not in the formal sense as defined by the US National Science Foundation, right? In some cases, they may lack intelligence. They might lack signal processing or the ability for control, right? And you could argue, well, a lot of that intelligence and control and processing is embodied in the soft material itself and in its ability to deform, and so that's a legitimate claim to make. Whether that would be something that other roboticists would accept, that's very much case by case almost, or depends on the particular subfields. What I would say though is that there's plenty of kind of embodiments within soft robotics, such as soft sensors and stretchable electronics that, I think we can all agree are not in and of themselves robots. I mean, we can call them robotic materials, but these are kind of like stretch circuits that are mechanically passive. They're not performing any mechanical action on the environment. They're not capable of any kind of motion on their own, but they're highly deformable, they're multifunctional, and they're capable of other types of electronic and sensing functionality. So, I would say, this is kind of my bold pronouncement, for this workshop, but, I would say to some extent, soft robotics, at least the robotics part of that, is a misnomer. And what I would be more comfortable with is to call the field soft matter engineering. I feel this is much more inclusive of a lot of the really, a lot of the amazing work that's being happening within the field. And, I'll kind of talk a little bit about what I mean by soft matter engineering, but really involves applications of condensed soft matter physics and soft material mechanics to problems in robotics, electronics, and engineering design. So even going beyond necessarily, more conventional kind of robotics applications or more formal definitions of robotics, it really is kind of basically engineering applications of condensed soft matter physics. Okay, so what do we mean by soft? I mean, there's plenty of metrics by which we can kind of distinguish between the kind of the stiffness or rigidity or kind of compliance and softness of a material, Young's modulus being just one of many different types of metrics. And kind of at a high level, soft matter engineering is really about taking materials that are on the soft end of the spectrum and integrating them in ways that they exhibit functionalities that we more typically associate with kind of more rigid, stiffer materials. And so, a challenge, of course, with integrating is that inevitably you are going to have cases of mismatches in size and in shape and stiffness of the materials. And so something that really stands out in soft matter engineering are the challenges with manufacturing and have these kind of material architectures and systems and devices that are highly heterogeneous in terms of all the different types of materials that have to be robustly integrated. And effectively, overall, globally, you would want these systems still to exhibit a lot of the functionalities that we see here, right? And these are, common among, soft biological tissue and organisms as well. I mean, ultimately, we want things, that are soft and deformable and kind of, satisfy a lot of the requirements that we need for applications in soft robotics. Let's see, there's some questions here. I don't know if this is, looks like there's a question here about what percentage of soft materials make a soft robot? And it looks like Mark Kokoski talked about selectively soft robots that combine both soft and rigid materials. So what I will say and why part of the reason that Mark Kokoski has been such an inspiration to me as an engineer is that this whole field. Well, he not just made pioneering contributions to soft robotics, but also the kind of the field of bio-inspired engineering and robotics. And I would say that within that field, in a sense, you could almost argue that from a timeline standpoint, it predates or kind of this current iteration of soft robotics. But a lot of the work in bio-inspired robotics does involve these kind of more hybrid type architectures where we're combining, in some cases, soft and compliant materials with more rigid materials, right? And so it's almost not really clear, whether we're talking, soft or, if those truly kind of satisfy the definition of soft robotics or not. What I would kind of say is kind of just going back to kind of my earlier definition. I would call it a soft robot if its functionality is primarily dictated by the mechanics of the soft material. If you're using soft materials just for the joints and the rest of the body is like kind of piecewise rigid, I wouldn't call that a soft robot. Yes, I mean the deformation and the mechanics of those of those joints certainly do contribute to the overall kinematics and mobility of the robot, but they're not kind of the primary influence on the mechanics, because those kind of piecewise rigid systems, their kind of kinematics and mechanics are also largely governed by the rigid elements as well. And so you can have soft robotic materials that are incorporated into these kind of hybrid robotic systems. I wouldn't call the full robot implementation a soft robot, but I would say that it incorporates soft robotic elements. And I think that kind of speaks to what Mark Kokoski had been talking about. And I would also kind of recognize that as an important trend within the field of bio-inspired robotics, where we're seeing kind of this broadening of material systems, where it's not just all made out of soft materials and fluids and granular matter, but also has kind of a rigid backbone, right? It has like a skeleton or kind of rigid elements that are kind of distributed throughout. So yeah, I would say that kind of incorporates soft robotic materials, but those I wouldn't necessarily call them on their own soft robots. Okay, so and again, just just put something in the chat or just interrupt me, and call out if you do have a question. Okay, so all right, so for the agenda, I'll just do a quick overview of what I think of as soft robotic materials. Really the core of this is going to be looking at the mechanics and thermodynamics of soft robotic materials. This is going to get really into a little bit into the weeds and into the underlying kind of principles. And apologies in advance if if this is either already kind of very familiar to you or you're just not interested in this topic. And I also kind of do my best to get through slides on just a little bit of the current work in my research group. And then I do want to close out by making a few remarks about the prospects for entrepreneurship and commercialization within the field of soft robotics and robotic materials. Okay, so real quick, an overview of soft robotic materials. I would say that robotic materials, kind of more broadly speaking, at least the way I've seen it treated in the literature, relates to materials that exhibit quote robotic functionality. So that's a bit of a circular definition there. But by robotic, I think we generally know what we mean here. We're talking about materials that are multifunctional. They also have the capabilities of actuation, sensing, and/or signal processing and intelligence. And so, this covers everything from stretch circuitry with embedded microprocessors to, soft robot, tactile skins to all sorts of different types of soft actuators. This is in contrast to a lot of kind of the more conventional materials that are used in robotics that are kind of single purpose. They're not multifunctional in the sense that they're only there for to say function as a hinge or to function as a casing or as a load-bearing element. And generally what I would say about soft robotic materials is that they're all stimuli responsive. So either they're actuators that move, change shape, or change stiffness in response to stimuli, or they could be sensors, sensing skins that basically produce some kind of signal in response to some stimulation or some sensor input. Okay, a great resource here is this paper by Kaushik Bhattacharya and Dick James in Science, where they kind of argue of kind of a new way of thinking about multifunctional materials, where the material is the machine. And so this is a paper that came out, well before the current interest in soft robotics and something that has been a big source of inspiration to my group. Okay, so this is just kind of a data dump here of just a variety of different material architectures used in soft actuators and in artificial muscle. I'm not going to kind of go through these. You'll probably be familiar with most, and also apologies that I don't have the names of all the different research groups associated with each of these subfigures. So what I would do is just ask you to kind of reference that review paper at the bottom that has kind of more of the details on what those references are. Likewise, in soft electronics and sensors, again, we see a wide range of different material architectures here. Okay, so thinking about kind of soft matter engineering now as kind of basically a foundation to create these kind of robotic materials. I mean, I would say to think about it kind of holistically, right? Not just about material architectures and compositions, but also manufacturing methods, material synthesis techniques, and also kind of what are the underlying principles in terms of the design and modeling, and also just the underlying physics of these material systems. And so this kind of broader framework of what I'm calling soft matter engineering for kind of robotic materials has its scientific foundations in these fields like I've talked about. Condensed soft matter physics, material science and chemistry, in which I would include polymer science and polymer engineering, thermodynamics and mechanics of materials, which is what I want to kind of focus on for this talk, and then also kind of advanced manufacturing techniques, and that I would include microfabrication, nanotechnology, soft lithography, all that. So these in my mind are kind of the scientific foundations, and really soft matter engineering is a field of applied science where we're kind of applying these scientific principles and methods to applications in stretchable electronics, soft robotics, and other kind of domains related to robotics. Okay, so what are the types of materials that we typically work with? Well, I mean, a lot of you are, of course, familiar with all the different types of silicones and rubbers and elastomers. I mean, there's also urethanes and fluoropolymers and a whole host of other types of materials that are typically used. I mean, when it comes to elastomers, we can kind of divide them into thermosets and thermoplastics. And these thermoplastics that are really popular in soft robotics, a lot of these are actually block copolymers. And when it comes to copolymers, I mean, you can engineer these with in all sorts of ways, and you can graft in functional groups, like conductive, components like PANI or PDOT, and you can kind of tailor the electrical and thermal properties of these materials. There's also shape memory polymers out there, materials like liquid crystal elastomer, LCE, that are also becoming quite popular in the field of soft robotics. So basically, one of the common features is that almost always you see kind of a soft elastomer as the carrier medium, and the elastomer itself could be mechanically passive, or it could have these shape memory properties, or these based tailored to have various conductivity. Soft robotic materials also typically have some kind of embedded active matter, and by active matter I'm speaking very broadly. I mean, it could just be the air that you pump in from a McKibben actuator, right? It could be a gas, a fluid. It could be granular media that's used today for particle jamming and stiffness tuning. It could be all the conductive powder that you mix in to create percolating networks for electrical conductivity, or creating dielectric type systems. There's been a lot of really exciting work with incorporating ferromagnetic and magnetized particles to introduce magnetic functionality, and of course there's also been really cool work with adding photonic materials for electroluminescent properties, or putting optical waveguides for introducing kind of optical or photonic functionality into these material systems. So this is at really high level. I mean, what I think about when I think about the different types of soft matter that go into these robotic materials. And in terms of applications, I mean, you've been seeing this throughout the workshop, how these types of material systems are used for tactile skins, artificial skins, stretchable electronics, artificial nervous tissue. There's plenty of exciting uses of soft microfluidics, and then biohybrid type systems, and of course soft actuators and artificial muscle. And again, I would say that the common feature in all these different application domains is that we this utilization of heterogeneous combinations of various types of condensed soft matter, and again that application of condensed matter physics has this kind of foundation in these various different fundamental principles. So what I want to kind of touch on next are how we use these principles of mechanics and thermodynamics to gain insights into the design and operation of these robotic materials. And these principles can be applied to a wide range of different material systems. And so I'll just kind of touch on a few of these, in particular pneumatics and also electrostatics and ferromagnetics, but they can also be applied to these other material systems as well. Okay, so moving on here, and again, apologies, I'm kind of rushing through these topics. I'm just trying to, this is a bit of a data dump. I'm trying to kind of cram a lot in, but really this portion here is really kind of the heart of the presentation. Okay, so just fair warning, it's gonna, this may or may not be different than some of the other presentations, in the sense that it is going to be almost kind of a little bit of a lecture style, and this is kind of adapted from content that I teach in some of the graduate level classes on soft robotics and kind of mechanics of soft systems that I teach at CMU. All right, so again, going back to how materials are presently used in robotics, kind of more generally. I mean, there's a wide range of different engineering materials, and we can kind of classify them in based on their stress strain behaviors, right? So there's of course the stiffer plastics and metals. That are kind of the load-bearing elements or kind of used as housing in robotic systems, and they tend to have a very steep curve when it comes to plotting stress versus strain. When it comes kind of to the other end of the spectrum here, we have kind of these softer materials like these elastomers that have basically a much more shallow slope and can allow for much higher strains. Now, what's not captured in this plot is this, not just the kind of the stress limit and the strain at break, but also the degree to which these materials are elastic. And by that I mean, when you unload these materials, does that stress strain curve kind of follow the same path that we saw during loading? And in a lot of cases, for a lot of engineering materials, we see inelastic behavior where we see a great deal of hysteresis. And that's oftentimes due to viscoelastic effects or due to plastic deformation, right? So this plot even doesn't fully kind of capture the range of different types of mechanical behaviors that we see. Let's see, I see there's a little stray mark here. Let's see if I can clear that or not. There we go. Okay, so that kind of gives a fairly wide picture of the different types of materials. And if you really wanted to kind of distill things down to just kind of one metric or one value, when we kind of compare the softness or stiffness of these different materials, of course, there's Young's modulus, right, which scales with the amount of force or stress it takes to kind of strain a material. And that generally I find to be a very useful metric for comparing the kind of softness of materials. And kind of soft robotics, typically we're working with materials that have a modulus more on the order of hundreds of kilopascals, right? At most maybe a few megapascals. And these are materials that are fairly elastic. They can be strained to about anywhere from 100 to 1,000%. And then going back to the earlier question about these kind of hybrid systems where we're mixing kind of soft materials with rigid materials. Again, by my definition, for the whole thing to be called a soft robot, the overall system kind of effectively has to have kind of this degree of compliance and deformability. Otherwise, basically, it's just a robotic system that has soft robotic components within it. Another metric that's sometimes used to talk about kind of the hardness or softness of material is this shore hardness. And there's actually different standards for shore hardness. I'm not going to kind of go into the details here. I just generally find this a much more confusing way to represent the stiffness of a material. But unfortunately, if you look at a lot of data sheets from distributors and suppliers of kind of engineering materials, instead of reporting the Young's modulus, they'll instead report a shore hardness. And then sometimes they won't even give you what the specific standard is. And so you kind of have to infer that just on your own based on context. So what I just talked about, that's more for kind of homogeneous materials. And of course, if you want to now functionalize these materials to tailor their dielectric properties, their electrical conductivity, their thermal conductivity, typically what we do is we incorporate different types of conductive filler. So these could be carbon black, it could be silver microflakes. I mean, there's all sorts of different types of carbon allotropes and metallic nanoparticles that you can kind of put in. And generally what we see are fairly common trends that with higher filler concentrations of these conductive powders, we can effectively get the composite to exhibit higher conductivity, but it's at the sacrifice of elasticity and compliance. Adding more filler is going to cause an increase in basically how stiff the material is, how brittle it is, and also to what extent we see inelastic behavior and hysteresis between loading and unloading. So in the literature, I found comparisons of shore hardness with Young's modulus. Not very good ones. I think if you go to like Wikipedia or something, there might be some equations there. What I do in the classes I teach is actually go back to kind of like first principles. I say that in quotes, but I just look at how shore hardness is measured, right? You have these different indenters. For OO, it's this hemispherical indenture. With shore D, it's a conical indenture. And you can actually study the mechanics of what the depth of indentation is as a function of the indentation load and also the geometry of that indenter. And you can relate that depth of indentation with the Young's modulus of the material, right? Hertzian contact theory is a perfect example, at least in the case of shore OO. And so the shore hardness is actually, these numbers are actually percent indentation. So yes, so it's actually the opposite. So if a material has a shore hardness of 100, that means that under this load with that indenter, there is 0% indentation. And if it has a shore hardness of 0, that means that there's like 100% indentation. So it's actually kind of swapped, a little bit confusing. But by looking at that percent indentation and relating that to the corresponding theory and contact mechanics, you actually can come up with a theoretical relationship between shore hardness and Young's modulus. So that's one way to do it. The other way is that there's just look at an empirical lookup table, right? I mean, people actually have experimentally independently measure the Young's modulus and measure the shore hardness, and then just have some big graph or mapping, between the two. Those are really crude, those mappings, but it might get you in the right ballpark. So again, I haven't really seen as much of that in the academic literature, but if you just look online, you'll see some ad hoc content there. Okay, so I've been talking about elastomers and kind of solids, but in soft robotics, we also care a lot about fluids, right? And for that, instead of using Young's modulus or shore hardness, we talk about the viscosity, right, and different features of the rheology of these materials. And certainly, I mean, there's kind of a very prominent role for different types of fluids in soft robotics. So here's just one example on the top of a liquid metal alloy that's kind of commonly used for kind of soft skins and stretch electronics. And I haven't seen kind of as much work within soft robotics, but there's been decades of research on electrorheological fluids and magnetorheological fluids that have these kind of phase changing and stiffness tuning properties in response either to electrical stimulation or magnetic field. And ultimately, you can kind of basically see or model and evaluate the kind of the rheology of these materials kind of in the context of these typical behaviors when we look at kind of the shear stress of the material as a function of shear rate. Okay, so kind of going back to soft robotic materials and really kind of delving now into the heart of this workshop. We're like 30 minutes in, and I'm finally kind of getting to the main point here, is that for virtually any, well, actually for all, I mean, in principle, for any soft robotic material system, we can always examine the mechanics and physics from a thermodynamic standpoint. We can always define a Gibbs free energy of the system. And we know that the Gibbs free energy is going to be subject to the first and second laws of thermodynamics. And so for a lot of these material systems, I mean, the Gibbs free energy is going to be related to the Helmholtz free energy and also the mechanical work associated with that system. And so when it comes to Helmholtz free energy, there's going to be an internal chemical bonding energy component, or like just like an internal energy component. And then there's also going to be a system entropy component to Helmholtz. And then with mechanical work, this can come from a lot of different sources. It could come from external loading, dead, really see but the dead load, but that mechanical work can also come from internal air pressure, or it could come from basically the Maxwell stresses that are induced by electrostatic charge, or from body forces from gravity or from electromagnetic fields, right? So this mechanical work can be a lot more than just surface tractions and mechanical forces that can come from other sources as well. Okay, so what we know from the first law is that in a closed system, that the Gibbs free energy remains stationary. So we have energy conserved within our system, and just knowing that the two main contributions are work and Helmholtz free energy, what that means is that any change in Helmholtz free energy has to be balanced by a corresponding change in mechanical work that's performed on the system. Okay, so that principle of kind of stationary potential is kind of represented here when we look at the Gibbs free energy as a function of whatever the variable is that we're defining as the state of the system. So if we're looking at our soft robotic system and looking how the radius, the inflation diameter changes, right? Then that would be the independent variable here that can change. Or maybe it's the length of elongation of our actuator, or maybe it's like the amount of voltage that's stored within our electrostatic transducer. Regardless of what that independent state variable is, we can always come up with this plot or this manifold of potential energy as a function of those independent variables. And what we find from the first law of thermodynamics is that slope has to be 0 at static equilibrium, right? So the potential energy has to be stationary. So basically that's another way of saying that energy is conserved. And the second law of thermodynamics, which relates to entropy in our system, that dictates that the Gibbs free energy has to be minimized. And so that basically the second derivative of that potential energy has to be greater than or equal to 0. So I call this the principle of minimum potential energy just because within mechanics and soft robotics, typically instead of calling it Gibbs free energy, we call it potential energy of the system. And so, what I just showed is just for a single, 1 degree of freedom system, but this could also just as well be applied to multi-degree of freedom systems, right? So where you have like length and radius and wall thickness and voltage and a bunch of different variables, all can independently vary. And so in those cases, you have to make sure that our Gibbs free energy is minimized with respect to all of those different variables. And of course, sometimes the variables could be, not scalars, but they could be functions or they could be tensors, right? I mean, your unknown variable could be the strain field, throughout the entire material, right? It could be like, or it could be the electric field or electric displacement, right? So in those cases, it's not just basically one scalar value, like a length, it's going to be basically strain, an infinite number of, strain values at all the different points within your elastic body. And for that, instead of using this Rayleigh-Ritz formulation, we have to use calculus of variations in the case of scalar functions, and then more generally tensor analysis and differential geometry when it comes to vectors and tensors that are free variables. So what I'm going to show is that how these variational principles can be applied to a variety of problems in soft robotics. I'll just kind of, very quickly just touch on these two different cases. So starting with just how we can go from the first and second laws of thermodynamics to deriving a constitutive model for a hyperelastic solid. And then, using these same techniques, we can see that they can be applied to McKibben actuators, dielectric elastomer actuators, also looking at ferromagnetic systems. And so really, this is kind of what I advocate above anything else. If you want to really study the mechanics and physics of soft robotic systems, use these energy minimization techniques. Don't waste your time with stress strain approaches or other methods. And I would actually say, don't even waste your time with finite element, unless you know specifically what that design is and what all the different dimensions are and what all the materials are, I mean, in those cases, sure, plug things into FEA and you can get your solution that way, but if you're still in the early stages of design and you don't even know what the dimensions are and what the geometry is, if you still don't even know what the materials are that you're going to use these energy principles to kind of just get a back in the envelope ballpark kind of intuition for basically what are the important governing physics of your system. So when it comes to hyperelasticity, how do these energy principles play out there? Well, I mean, let's just look at the most popular material in soft robotics. Let's take a look at silicone, right? Or more specifically polydimethyl siloxane, these platinum cured silicones. They have all sorts of different brand names, and there's everything from Silgard 184 to all the EcoFlex products that that have been at least in the States we have from the company Smooth On, all sorts of different vendors and suppliers and different types of molecular weight ratios and cross-linking densities and additives and all that stuff. But basically the underlying principle here is the same, that we have this new loose network of polysiloxane chains. Okay, and so each of these polysiloxane chains are composed of these siloxane monomers, and these kind of monomers, or these kind of units within our polymer chain, can, we assume, just freely rotate with respect to each other. And then periodically we have these kind of covalent bonds, these cross links that connect adjacent chains, right? And it's really those cross links between the chains that give the rubber its kind of material elastic integrity. But what makes it kind of resistant to mechanical deformation is actually a very interesting kind of a principle that's really steeped in the entropy of these material systems. And so it does kind of go back to this representation in terms of a Helmholtz free energy and a Gibbs free energy for the system. And so we know that these polymer chains are composed of n number of these short kind of monomer segments. And each of these chains can, take on just actually in principle, an infinite number of different configurations. So to make the problem more tractable, we assume that there's only a finite number of configurations that these polymer chains can adopt. And then from that number of configurations, we can identify an entropy associated with that system. And then to basically get the force required to stretch the material, we go back to that energy balance to relate mechanical work to the corresponding change in Helmholtz free energy. And assuming that the covalent bonds within our polymer aren't really stressed that much and they kind of maintain the same length, really the deformation of these soft material systems are going to be largely governed by the kind of the unwinding or uncoiling of these polymer chains, or the rotation of these adjacent adjacent monomers, right? And so in that case, really the change in Helmholtz free energy just corresponds to the change in entropy of the system. And so when we think about entropy, again, we think about all the different possible configurations that each macromolecular chain, each polymer chain can adopt. Boltzmann's constant, factors into this as well for getting that entropy. And then when we, look at, okay, well, what is the entropy? What are all those different, possible configurations? For that, we turn to statistical mechanics. And so, from that, we can kind of get this simple expression here that relates entropy with the overall volume of material that we have. So that has X, Y, and Z dimensions. And then it also has kind of values like, there's the total number of polymer chains, again, Boltzmann constant, this kind of root mean squared average of the end-to-end distance of an average chain. And then also this value M naught, which just corresponds to the number of possible configurations that a chain could have in the special case when the two ends are touching each other. And so based on that, we end up with this kind of representation. And if we now take this volume and deform it, we can relate those dimensions, the X, Y, Z components of the volume with stretch. And in the case of uniaxial loading, right, we stretch along the X direction, which means that we have to contract along the Y and Z. We get the corresponding change in entropy, plug this back into our energy balance, and then that gives us a relationship between force and stretch that turns out to have a form that looks like our familiar expression for a neo-Hookean solid. So this is kind of the foundations of hyperelasticity, all kind of originating from principles of thermodynamics, and statistical mechanics, where we have this coefficient of elasticity now C1 that's related to all these intrinsic properties of our polymer. And so we can kind of take this and now generalize it. I mean, this is just a very simple application of statistical mechanics. I mean, we can make this fancier. There's the Arruda-Boyce model that Mary Boyce and Ellen Arruda developed that also takes a similar approach, but ends up with a much more accurate constitutive model for stress versus strain, or stress versus stretch. And what's also significant is that from that entropy, we get our Helmholtz free energy, and from the Helmholtz free energy, we get our elastic strain energy density, which sometimes appears as W in the literature. So now kind of empower this value, we can do all of these robotic systems and come up with a expression for our Gibbs free energy. So in the case of a pneumatic artificial muscle, we again have the entropy of the rubber that's captured here by the strain energy W. Again, we see that C1 constant, we see the stretch components kind of factor in. And then we also have the mechanical work terms, right? That was the other important component in our potential energy, right? And so here we have the mechanical work of that applied dead load, right? That's given by F times L. And then we also have the mechanical work associated with all that internal air pressure. And so when we minimize our potential energy with respect to the overall length of our actuator, we end up with solutions that turn out to be in very good agreement with what we observe experimentally with these types of McKibben actuators. Just in interest of time, I'm just going to kind of speed through this. Same goes with dielectrical elastomers, right? Here again, we have elastic material. So we have our strain energy density that we're going to plug into our Gibbs free energy. Here now, instead of mechanical work associated with an internal air pressure, we have mechanical work associated with all that electrostatic pressure, what's sometimes called the Maxwell stress. And the way that that's reflected in the Gibbs free energy is this term that's known as the electrical enthalpy. And so something that I'm kind of hand waving and not really being super careful about is that these different terms in our Gibbs free energy, depending on what we use, what we select as our input variable versus the independent output variable, that's actually going to influence basically how we define the different contributions of mechanical work. And as we switch what those variables are, we have to perform what's called a Legendre transformation in order to kind of update those contributions to the Gibbs free energy. And so when it comes to electrostatics, sometimes you'll see this electrical enthalpy is replaced with a different kind of electrostatic energy term. And that happens if instead of voltage control, we decide to kind of operate this with charge control. And so that's just simply arises from that Legendre transformation. Regardless, I mean, that's just kind of a side point here. Again, same principles as before. We have our Gibbs free energy, and now we just minimize with respect to our independent variable. And that variable in this case could be length, or it could be that longitudinal stretch lambda. And when we do that, we get this result that again is in fairly good agreement with typically what we see experimentally. Now, kind of another outcome of this is that we see this instability within dielectrical elastomer actuators. This is something anticipated by our thermodynamic formulation, and it's also something that we see experimentally as well, right? And so, here's a case of a dielectrical elastomer actuator where at some point you're going to see this electromechanical instability that's going to result in this dielectric breakdown of the material. So you'll kind of see that there's that little spark there in the corner. I'll just kind of play that again, just so you can see that. And so that just arises from this instability that we get, that as we apply voltage and our actuator starts to contract, that contraction results in greater internal electric field, which results in more contraction, and you end up with this kind of positive feedback loop that ends up wanting to squish the rubber so much that it eventually undergoes this electrical breakdown. Last quick example here is to look at ferromagnetic elastomers, and so this is actually an example of work from my lab. This is by Vivek Ramachandran, a former grad student in my group, that looks at the snap-through instability of these ferromagnetic elastomers. So the rubber basically has these ferromagnetic particles in it that undergo basically attraction to this external magnet. So as we bring this magnet closer and closer, that magnetic force gets larger and larger, and at some point it overcomes the elastic restoring forces in the rubber and causes a snap-through instability. Again, we can examine this using the exact same techniques as before. We have this Gibbs free energy. Again, there's this elastic term. Here we have now a mechanical work associated with gravity, because these magnetic rubbers are fairly dense and they get weighed down a little bit. And then we also have a work term associated with the potential from that electromagnetic field, right? So that magnetic force is going to exert basically this body force on the rubber, and that's going to be incorporated in our Gibbs free energy as well. Again, same as before, we're going to minimize to basically get the state of the system at static equilibrium. And snap-through instabilities occur basically when we have an instability, right? When we violate that second law of thermodynamics. And so that occurs when the second derivative of potential energy with respect to our amplitude is less than zero. And so to avoid that snap through, to maintain a stable state, we have to kind of make sure that the potential energy has this basically positive curvature. But then if this magnet gets too close, then we end up hitting some critical kind of distance at which that condition no longer applies and the snap-through instability occurs. And here, without any data fitting, we actually find that these predictions from thermodynamics and these energy principles are in fairly good agreement with what we measure experimentally for snap-through instabilities, for what that critical proximity is of the magnet, at which point we see it kind of pop into this other configuration. And what we're plotting here is basically what that critical distances of the magnet as a function of just some geometric features of the initial amplitude of the buccal strip of rubber. All right, so I have a few minutes here, so I'm just going to kind of speed through just a little bit of some of the stuff that we're doing in my group. I mean, we do. Hopefully, this doesn't crash my computer here, but this is just kind of a bunch of videos I'm going to try to play simultaneously of, for the most part, untethered soft robots that are powered using shape memory alloys. So we're doing a lot of modeling, simulation, and then kind of closed loop control of these systems, doing a lot of investigations of path planning. Some of this is model based, some of it is using kind of learning based schemes. So this is kind of one just set of projects in my group. I'm happy to chat about a little bit later. Another thrust of my lab are these wireless and wearable sensing skins, these kind of sticker-like architectures for health monitoring and physiological sensing, using all sorts of different types of stretchy circuits. Here's kind of an example of a soft robot tactile skin using magnetic microparticles. This is something that we've actually been spending a lot of time recently looking at. And these actually have been the focus of a lot of our work on using kind of supervisor-based algorithms and kind of applications of machine learning in terms of establishing the mapping between pressures, surface forces, and also kind of robot function with the changes in internal magnetic field that arise with these magnetized elastomers. We also do quite a lot of work with liquid metal. So here's just kind of examples of using liquid metal as electronic skins with different types of embedded microelectronic chips for sensing and signal processing, and using that in these different types of soft robotic systems. And also just creating multifunctional rubber composites where we use liquid metal and other types of materials just to tailor their electrical, thermal, and shape memory properties. So I'll just kind of quickly speed through this. And so these material systems have all sorts of very robust mechanical properties. So not only are they soft and stretchable, but in some cases, they have mechanical and electrical self-healing properties. Sorry, these videos don't seem to be let's see if I can get these videos to run. Sorry for this. But just kind of more examples of kind of combining liquid metal with materials that allow for 3D printing, and then in the case of liquid metal combined with liquid crystal elastomer. And then lastly, we've been also doing a lot of work with applying these material systems for energy harvesting applications, whether it's triboelectric and generating energy from body motion, or thermoelectric, generating electricity from body heat. And lastly, I forgot that I added this slide here, but we're also doing quite a bit of work now with hydrogels, combining it with silver powder, liquid metal, and other types of functional materials to achieve highly stretchable, mechanically robust, self-healing hydrogel-based composites that also have very high electrical conductivity. So it looks like I just have a few minutes here. I mean, do stop me if you have questions. Otherwise, what I was just going to do is spend the last few minutes just talking about entrepreneurship in soft robotics. And I'll just kind of blaze through this. I mean, a lot of these are just kind of more high-level thoughts, but just to reemphasize, there has been a lot of kind of exciting progress lately in companies that are commercializing a lot of these kind of soft material architectures and using them in a variety of different practical applications. And so we are seeing a tremendous amount of market growth within this field. And so this is soon poised to be a multi-billion dollar industry. And that growth will kind of, hopefully continue, right? So it will actually become hopefully eventually an important segment or subsegment within the field of robotics. My own lab has actually spun out a few companies that are trying to commercialize various types of soft robotic material systems for biomonitoring and sensing, for bringing the thermal properties and using these in a variety of different applications. And also, looking at stiffness tuning materials and also looking at kind of electrostatics for various types of clutches and actuator technologies. And so, these are all companies that, we actually are looking to hire. And so we've had good traction with customers and investors. And so, more than happy if you do want to reach out to me, if you are interested in internships or maybe even just a full-time job after you graduate, I would be delighted to talk about potential engagements there. But just kind of more generally speaking, what I've learned through launching these various startups from my group in partnership with my former PhDs and postdocs is that soft robotics, at the end of the day, we're talking for the most part hardware technologies, right? I mean, there's a big algorithmic kind of element to a lot of these implementations, but at the end of the day, we're talking about novel material architectures. And as a hardware company, we have to deal with the difficult task of getting these material systems qualified, right? We don't have the luxury of just rolling out some software and basically learning on the fly and putting a product there that's not maybe perfect and can kind of get reiterated as it's used. For a lot of these customers, they want to be guaranteed that these materials are going to and these material systems are going to work every single time within their products, and so that pipeline for qualification does take quite a number of years, right? And it kind of involves all of these different steps in terms of efficacy and repeatability and manufacturing scalability. And once you have the manufactured, system, or mass manufactured, product, is it resilient? Is it reliable? Right? Is your supply chain, reliable as well? I mean, are you guaranteed that you're going to still be able to count on all those raw material suppliers to be able to provide you with the materials you need for your product? And so you end up with this chicken and egg dilemma, right? I mean, you can't really get any revenue from customers until you've gone through the entire pipeline that I just talked about. But you can't get that kind of product qualification. You can't get through that pipeline until you have investment and funds in the company. And unfortunately or perversely, you can't get investment until you have revenue. In a lot of cases, right? And so, there are, solutions out there that I'm more than happy to chat about offline in terms of ways that you can overcome that chicken and egg dilemma with launching a startup. And these have been secrets of, or I shouldn't say secrets, but these have been recipes of success for a lot of startup companies that I've seen. So more than happy to kind of talk about these. So just a few minutes left, so I'm just going to wrap up there and happy to take any questions. So thanks so much for your attention, and apologies, for kind of bouncing around a little bit with these different topics, but hopefully some of this information was useful. There is a question in the chat box about ferromagnetic elastomers. What applications can snap-through instabilities serve? No practical applications. I mean, we demonstrated ability to make a switch that uses that snap-through. I didn't show it in the slides, but if you look at the journal publication, we basically are able to kind of have this magnetically controlled circuit switch. But it was more kind of a mechanics exercise. I mean, I wouldn't claim that there's any practical applications, at least that we've identified with those types of material systems. Other questions?
So yeah, first of all, thanks a lot for the great talk. I was impressed that you combined fundamental thermodynamics law also with applications, products, and also entrepreneurship. I'll look in the room first for some questions, as the ones in the chat were already solved, I think. So are there some questions? Yes, Norma?
Thanks so much, Carmel. I have a question for you for the intelligence, because you have been developing in kind of intelligence material. So for you, physical intelligence so far, do you believe it should be more in material development or architecture? Which more significant to you in the design?
That's an excellent question. I mean, my own personal bias and take is that I think a lot can be done at the material architecture level. I don't think you have to engineer like new types of polymers or new types of fluids or kind of constituent elements. I think you can take existing materials and just kind of mix them and combine them or pattern them in ways to get basically kind of intelligent properties at the kind of meso and macro scale. And so, I mean, I think kind of a lot of the work with metamaterials and I think there's kind of a really exciting pathway there. It's not really my own research, but I think that's kind of one direction. But yeah, I would say that a lot of these materials that combine, say, liquid crystal elastomer, with liquid metal, or the hydrogels with just silver flakes, these materials do to some extent exhibit some degrees of intelligence, and we can accomplish that without having to engineer some new type of polymer or synthesize some new type of nanoparticle. Very good question, and still very much an open question as well. A lot of people would disagree with me on that, especially within the material science and condensed matter community.
Some other questions. There is a personal question in the chat. So the question is, thanks a lot for the wide topic presentation. Just a curious question. Would you say you are working more on the fundamental research level or on the application side?
I'm definitely working more on the application side. I mean, I would say, well, it's all relative, right? I mean, to a material scientist or a chemist, I mean, I'm definitely far on the application side. To a roboticist, I mean, they might think that I'm kind of more on the fundamental side in terms of really focused more on the materials and mechanics. And so, yeah, I would say that from a robotics standpoint, I would say that what I'm doing is kind of more basic research. I think that's a fair statement to make.
Okay, thanks a lot. Some other questions? If not, I want to thank you again with everybody here in the room. So,
all right, thanks a lot. It's my pleasure.
Can you hear me, Sepa?
Sorry?
Can you hear me?
Yes, I can hear you.
So, if possible, I would like to ask a question also. So, thanks a lot for the talk, Carmel. Actually, I really liked your presentation, but I would like to somehow criticize the first part. Actually, I have a question of you because you're talking about soft robotics and soft matter engineering reminds me for a current discussion about the topic, and the topic was is in the next year soft robotics be an independent field or a dependent field in robotics? So from that question, I couldn't understand the result or what comes out of this discussion, of a long discussion. I would like to know, what do you think about if we say soft robotics, if we say soft material engineering, what is the difference?
Yeah, I would say that the reason I call it soft matter engineering and not soft robotics is I feel like a lot of what we call soft robotics today, and I do like the more inclusive definition, but they're not really kind of robots, or they're not really robotic systems. They're basically, I wouldn't call like a stretchable circuit, or I wouldn't necessarily call that a robot. I would say even actuators necessarily, just that, capable of things that are capable of motion. I wouldn't really call those robotic systems as well. So if we try to keep or pigeonhole soft robotics as a subfield of the field of robotics, I feel like that might be too limiting. I also feel like it also is not reflective of the organic origins of the field of soft robotics. It wasn't an outcome of historically of the robotics community. It involved a lot of folks from kind of outside of the community. And so I think just to kind of be inclusive of not just future soft roboticists, but also the pioneers of soft robotics, I think it would be better served if it was its own separate field and not forced to be a subset of robotics. I'm sensitive to this because at Carnegie Mellon, we have the Robotics Institute, we have a big kind of robotics program here, and you do not want to be beholden to the broader robotics community in terms of defining the direction of your field. You want that freedom to basically chart your own path.
Thanks a lot.
Okay, are there no more questions? Or there's another question in the chat. Do you consider using more accessible natural materials? So looking at materials, like bio-based materials or natural materials?
Yeah, I do. I think for a lot of you who are looking for the next big thing in soft robotics, I mean, one of them is sustainability and looking at materials that are recyclable or kind of environmentally friendly, environmentally sustainable. A lot of funding agencies are actually making that a requirement, more and more for a lot of what they're kind of willing to invest in and support. So yes, I obviously natural materials is a very good path, to creating robotic systems that are kind of more environmentally friendly and sustainable. So I would say that there's also this whole other field of biohybrid, robotics and tissue engineering and all that stuff that of course involves kind of combining the biological materials with synthetic systems as well. I mean, the goal there isn't necessarily sustainability, but I think that's also an exciting direction too.
Okay.